This module also covers the problem of unsupervised learning, but this time we have a look at another non-parametric technique named hierarchical clustering.
A possible drawback of k-means is that it requires fixing the number of desired clusters. However, in some applications, this is an information that we do not have. Actually, it might be of primary interest of the analysis to discover how many subpopulations we have. Hierarchical clustering is a non-parametric clustering algorithm which does not pre-specify the number of clusters. The only needed input required is a similarity matrix. A similarity matrix is defined to be a squared matrix of size n, which is the number of objects to be clustered. Each entry of this matrix must be equal to the distance between any pair of observed data. Similarly to k-means, such distance may be the Euclidean one or any other notion of distance. Such similarity matrix D defines how close objects are regardless of their cluster assignment. To run the algorithm, we also need to specify a notion of distance between clusters. The most commonly used is the complete linkage distance, which defines the distance between two clusters to be equal to the maximum distance between two of their points. Looking at the example in the slide, the distance between those two clusters will be equal to the distance between the 2 points connected by the red line. Another example is single linkage, which instead only takes into account the minimum distance between points in different clusters, hence it is more sensible to noise. Here we briefly discuss how the algorithm proceeds to find the final partition. First, it starts putting all points together in a single cluster. Then, such big cluster is split in two smaller clusters, which must be as far as possible according to the notion of distance between clusters we introduced in the previous slide. This step ensures that the two subpopulations will be as much heterogeneous as possible. Finally, such step is repeated until each object forms a cluster of its own. Differently from k-means, we know that exactly n steps will be performed. Hence, if n, which I recall to be the number of points in the analysis, is large, this procedure can be very slow. This approach is known as top-down or divises clustering. It is not the only possibility, the opposite strategy is also possible. The final output of hierarchical clustering is a tree, named dendrogram, which is displayed in the slide. The idea is that this tree must be horizontally pruned to identify a specific clustering whose number of clusters is equal to the number of branches that have been cut. An example will follow in the next slides. This object is crucial also to identify the best number of clusters to represent the whole population. Indeed, the longer is the branch of the tree, the stronger is the evidence that for the corresponding number of clusters to be the most suitable one for our data. Let us see together some examples to better understand. Let the red line represent the eye where we want to cut the tree. By pruning it in that spot, we would only select two clusters because the red line intersects two branches. This is the most suitable partition for our data because the branches are the longest of the tree. Indeed, this is a very similar partition to the one we obtained using k-means for k equal 2. For example, if we had cut slightly below, then we would have selected 3 clusters. According to the dendrogram, this solution is worse than the previous one because the branches are shorter. My suggestion is to always visualize the partition you are selecting, or at least some statistics related to it. Indeed, in cluster analysis, it is important to have interpretable clusters, but if we look at the plot, it would be difficult to understand why the red and the blue dots are not part of the same population. Finally, here is a third example to understand a limiting situation, that is, when we are cutting so that 5 clusters are selected. The model is probably overfitting the data, selecting very small populations. Keep in mind that the higher the number of clusters, the more difficult it is to give a reasonable interpretation of all clusters. Usually, a relatively small number of clusters is preferred.
And now, let's see this new technique in practice and compare it with the results obtained using the k-means. For sake of comparison, we use the same dataset we used in the previous module about k-means. I recall you that when we solved the problem with k-means, we repeated the analysis for different values of k. This approach may be suitable in this simple example, but in general, it would be better to have a more general tool to identify the correct number of clusters. Hierarchical clustering is perfect for this task, since it does not need to pre-specify the number of clusters. Indeed, the only input it requires is a dissimilarity matrix. This slide shows how to perform hierarchical clustering with R. It is a very simple to use since it only requires a single output, which is the dissimilarity matrix. To compute such matrix, it is enough to use the dist function on our data. This function automatically computes the distance between each possible pair of points in the dataset. We save the return object in a matrix named distance, which is indeed the only input we need to provide the hclust function. That is the function that performs hierarchical clustering. We run this function and save its output object in a variable named fit_hclust. To visualize the dendrogram, it is enough to plot such object using the usual plot function. This could simply be done writing plot open bracket fit_hclust close bracket. The remaining options have been added only to show a better looking plot, but they are not mandatory. Moreover, we can use the rect.hclust function to visualize the level where we want to prune the tree. To use it, it is enough to put the fit_hclust object as first option and select the number of clusters we want in the second option, named k. In this case, we select 3 clusters because it is the partition associated to the longest branches. This produces the 3 rectangles displayed in the figures. Finally, to actually prune the tree and select a possible final partition, we must use the cut tree function. This is used exactly the same way as rect.hclust. Its output, named estimated underscore clustering, is a vector containing the labels that define the final partition. We can plot it exactly like we did in the module for the k-means. Please go back to slides in such model to check how to modify this code to adapt it to your problem. The final partition is indeed the same one we obtained using k-means, with k equal to 3. In general, it is possible that the two algorithms find different solutions. However, this example is so simple, clusters are so well separated, that both arrive to the same conclusion. And now it is your turn. I give you data and ask you to repeat what reported in the previous slides. Data are taken from a medical study which aims to cluster patients who underwent thyroid operation. Your task is to perform hierarchical clustering analysis and choose the most suitable number of clusters for your problem.